Good morning. My name is Joel Hartel. I work at the Fluke Corporation as a vertical specialist in our oil and gas group, and today I'm going to be discussing differential pressure meter gas custody transfer calibration and how to use your test tools in order to get the best custody transfer calibration you can. So what we're going to talk about today is three main areas. We're going to have a quick introduction, which is only going to take about 5 minutes, on why calibration matters in custody transfer. We're going to talk a little bit about differential pressure meters versus ultrasonic. We're going to mention a couple other meters while we're at it. We're going to spend the bulk of the presentation on test tool considerations. So we're going to talk very deeply about pressure calibration test tools, temperature calibration test tools, and then we're going to go into an extensive discussion on the various types of specifications of calibrators and what they mean for the end user. Last, we're going to cover what I call curriculum topics. This is primarily going to be a process overview along with some of the considerations for both the unit under test and how to be safe under high pressure circumstances. This will also only take about 10 to 15 minutes. Overall, this webinar should take about 45 minutes. So let's jump right in. So why does custody transfer matter? Or why does calibration matter for custody transfer? Well, custody transfer is, as the presentation says, the cash register. Fundamentally, it means that because we have such high volumes going through pipelines, even small errors are going to have significant financial impact. And there's a lot of contracts written around custody transfer. They're written around either mass or flow rate. They describe the BTU value of the gas to be transferred, and there's frequently a turn-down specification, that is, how much the maximum flow can be from the minimum flow. And these are all specified in legal documents. Typically, a custody transfer meter will actually have, there will be multiple transfer meters at a particular location, and they all need to agree with each other. There will frequently be meter provers installed as well, and if everything doesn't agree, a dispute will arise. What will end up happening is that when that dispute arises, your calibration records are frequently very important inputs into resolving that dispute. Who's right, who's wrong, who pays who owes what. And so the quality of your records matter a great deal, as well as how did you calibrate them? What are the procedures you used? Things like the API standards can help you with the standards portion, but your calibration records are going to be critical inputs. Well, obviously, I can't go into too much detail. We have seen several instances where calibration records were inspected as part of the dispute resolution process, and they're a very crucial record. I'll talk a little bit about documentation later. But primarily now at this point, it's why you need your good calibration records in order to support your custody transfer claims. The focus of this talk is going to be on flow rate. Fluke specializes in pressure, temperature, and electrical measurements. We don't do a lot of work around gas sampling. There are, of course, many potential errors in your gas sampling, and as that BTU value is frequently specified in the contract, that's a separate area, so that's going to be out of scope for this particular discussion. So what are the various types of meters that are out there? Why differential pressure? Why not ultrasonic? Well, ultrasonic is very well suited for interstate and intrastate pipelines. High flow rates, you're covering a long distance, you don't want large pressure drops, you really don't want to have to shut the pipeline down to do maintenance. And obviously the fewer moving parts you have, the less likely it is that the unit will fail. The other thing that's really nice about them is they have wonderful turn-down characteristics. You frequently can get 50 to 1 in an ultrasonic meter, whereas a differential pressure meter might only be 3 to 1. There's, as I'm sure a lot of you have heard, there's a lot of buzz about ultrasonic meters, what they can do for you, and the manufacturers of these meters are pushing very, very hard for them to be introduced. And yet, after all of this effort, while as much as 50% of the dollars spent in a given year are on ultrasonic meters, they're only 5% of the units. About 90% of the units sold today are some form of differential pressure meter. Why? Well, we've got a lot of history with them, so they're cheap and they're simple. There's a large replacement market that comes from the previously existing install base, and they're very well understood. We have a great deal of data, as well as well-written and well proven standards across the industry, across the globe, that allow us to do that. I've listed some of these standards here. I'm not going to go into a tremendous amount of detail on those standards. I would obviously anyone who's a specialist or a professional in this area should be very, very familiar with these standards. One other portion about differential pressure is that, especially with what we're seeing in the fracking industry, differential pressure meters are relatively accurate with wet gas. Some guys at CZ did a paper last year at the American Society of Gas Measurement and Technology, and they basically said they could correct to within 2%, which is something that the average ultrasonic meter very much would struggle with. And so they've got some very nice characteristics for gathering pipelines or things that are upstream of a processing plant where you might have water or other contaminants in your gas flow. So let's talk now about selecting test equipment. So let's talk about the types of pressure calibration test tools that are out there and some of the advantages and disadvantages of each. So by far the most common are electronic calibrators. The big advantage for them is they're very easy to set up and read. They don't require a lot of specialized knowledge to use. There are a bunch of manufacturers in this space, and several of them have given you a choice of % full scale or % reading plus floor. We'll go into that in some detail. There's also a lot of existing choices for pipes and fittings. A lot of the manufacturers who make the calibrators will also make the pumps and fittings to support it. Pretty much the two most frequent kinds you'll see will be pneumatic or hydraulic, and you can get any variety of fittings to meet your tubing and connection needs. So there's a lot of good stuff available out there. We'll talk a little bit about deadweight testers. Deadweight testers actually provide highest possible accuracy. So obviously we talked before that because it's the cash register, even small errors have an outsized financial impact. Deadweight testers can give you the best possible accuracy. The caveat to that is it's only under the correct conditions. So for example, the unit needs to be level. You'll need to make an adjustment for local gravity. Making an adjustment for local gravity can be quite challenging. If you are more than 3,000 feet above or below where the unit was calibrated, or if you are more than 3 degrees outside of the latitude of where the unit was calibrated, you'll have to make an adjustment. If both your altitude and your latitude have changed, there's actually a formula that you have to calculate in order to determine how far away you are and if you need to make an adjustment and how big that adjustment needs to be. It's very, very difficult for all but the most skilled techs to get this calculation and the leveling and all of the other things that need to be done exactly right in order to achieve this maximum accuracy. And frequently under field conditions, it's just not possible. You're working out of the back of a pickup truck, and even if you work very, very carefully, it's virtually impossible to replicate the accuracies that you would find in a lab. And so frequently, even though deadweight testers has a great deal of potential, under field conditions, they're usually not as accurate as an electronic calibrator. Two other small things. Because the unit will compensate for a small leak, which is actually a benefit when you're in the lab, it's actually a problem when you're in the field. It's harder to detect leaks in your setup, and obviously when you're setting up and tearing down pretty frequently, it's easy to introduce leaks, and it doesn't account for the pressure drop in your test hoses, which means that you have to calculate that yourself. The other thing it won't do is, because it's compensating, if you actually have a leak elsewhere, say for example in your meter, if you can't really see that, if you haven't isolated it and your leak check wasn't thorough enough, when you reset it up, frequently with an electronic pressure calibrator you can watch the pressure drop. However, if you do it with a deadweight tester, you may have some trouble determining if you actually have a leak or not. And it's very expensive to have to go back out there and do another check, because the person who will catch it will be your measurement balance engineer, who will look at your data and say, wait a minute, why is this unit drifting over time? Moving on to temperature calibration test tools, we're going to talk about 3 main types. The main one that people will use will be a precision thermometer. They basically will be a specialized tool, although some manufacturers have actually integrated a precision thermometer into an electronic pressure calibrator to make an all-in-one tool. They'll primarily use an RTD probe. The probes are assuming they were designed for an industrial application, are usually quite rugged. However, it is possible to damage them, and you should spot check them periodically. The easiest way to spot check them is something with like a dry block calibrator. So the dry block calibrator here I've got pictured. You actually can insert your RTD probe and verify that it's reading a correct amount. You'll set the dry block calibrator to hold a particular temperature, and then you'll verify that your precision thermometer and RTD probe system are working properly. Actually, the unit that is shown here can also verify installed probes on the pipeline. If you use this one, for example, in conjunction with a documenting process calibrator, it actually can auto-control the dry block, and you can insert your transmitter into one of the wells and basically allow the unit to auto-calibrate. And so it's something that you can actually set up and walk away from and have the unit basically verify that the transmitter is correct, or excuse me, that the probe is correct prior to reinstallation in the line. Last but not least, we'll talk a little bit later about low flow conditions, but under certain low flow conditions you can't trust the RTD probe meter, and you actually have to simulate it. So I've got a picture here of a RTD simulator. They will actually simulate the signal into the flow computer, and that will basically allow you to complete the calibration despite the fact that you can't get an accurate temperature measurement, or a representative temperature measurement, excuse me, not accurate. However, it does not verify that your RTD sensor is actually functioning properly. So if you're going to use a simulator, having a dry block calibrator can be a very handy thing to ensure that both the probe and the transmitter are effectively calibrated. The last thing is that the latest version of these electronic simulators are every bit as accurate now as decade boxes. And so they're a very high accuracy tool, and they are very useful. So we're going to talk a little bit now about percent full scale versus percent reading plus floor. So in the old days, analog sensors were all specified in percent full scale. Well, digital is a different technology, and it's basically allowed manufacturers to try other ways of specifying. And one of the more common ways you'll see is to specify a percent reading plus floor value. And the idea here is that it allows you to get away with one of the big disadvantages of percent full scale, which is as you move higher in the range, your accuracy will effectively increase. But the reason I say that is that when you have a low value, a percent full scale will have a constant error across its range, whereas a percent reading plus floor will actually have a lower error value. So what that gives you is it basically allows you to say, okay, I don't need to worry as much about picking the lowest possible range for the work that I'm doing. I can pick a unit and use it across. For percent full scale, that's not an option. However, there are some other strategies for percent full scale that you can use. So for percent full scale, as we discussed, because the error, it relates to the full scale value of the unit, basically you want to pick the lowest possible value that you can get away with. And what we'll frequently recommend for people who are looking at a unit like this is to say, well, pick the unit that is at about 80 to 90% of the work that you do. So let's say you primarily are working at 12 to 1400 psi, and then every once in a while, 1 out of every 20 transmitters, you might get up to 1850. We'll recommend picking a pressure value of 1500 for most of your work, and then having a separate pressure module that will cover that higher scale on the rare occasions that you actually need it. This will give you better overall accuracy across most of your work, and then when you do need that additional work in those higher ranges, you can get it done. So what's the disadvantage of percent reading plus floor? Well, the bottom line is that the percent floor spec is not always achievable. There are many things that can influence the total error that you actually see. And so even though it would appear that the unit is very accurate, it's very easy to get outside of either the operating conditions, or perhaps you have a leak and there are other problems, and you can't achieve that floor spec. A great example of this is if you take the unit, and in a lab, there's no question that a unit will be able to achieve this floor spec. But if you just take it into your living room or your kitchen, you turn the unit on, place it on the table, hit the 0 button, and walk away. If you sit there, you can actually watch the 0 shift. And your living room is nowhere near as rugged as the field can be, and so it can be very, very hard to really achieve these values in the real world. So what's the bottom line? Basically, the calibrator, it's accurate. The more accurate and precise it is, the better it is. But the real requirement actually relates to how accurate your calibrator is compared to the transmitter that you're trying to calibrate. We're going to talk quite a bit about this here in a few minutes, but just keep in mind that raw accuracy isn't enough. It's the relative accuracy between your calibrator and the unit under test that really, really matters. So let's compare two calibrators that have these different use these different specification methods in order to determine which one is more accurate at various points. So here you see a graph of two calibrators, A and B. Calibrator A is specified as a percent of full scale. Calibrator A is the yellow line. And then you have calibrator B. Calibrator B is specified as a percent of reading plus a floor spec. It's the red line. On the y-axis, you'll see the spec error. So the higher the number, the worse it is. So the line that is lower is better. And this is done over a range of units from 0 psi all the way up to 1500 psi. These two units are real calibrators. I'm not going to mention who manufactures which one because the point is to compare the specs and the advantages and disadvantages of both. So if you look at, you're trying to look at the lower line as the better unit. So here you'll see that calibrator B, specified as a percent of reading plus floor, actually is better over the bottom third of the range. However, calibrator A, specified as percent full scale, is actually better over the upper 2/3 of the range. So depending on the values that you're trying to calibrate, it actually will change which calibrator and which specification type you'd like to have. This is why when you're picking a calibrator that's specified as percent full scale, it's so important to pick the lowest one that will cover the majority of your use cases. It gives you a better error, and it basically moves this yellow line down and allows the calibrator to actually have higher accuracy over a larger portion of the range. This graph is pretty easy to understand and is pretty well defined, but as I show you in the next graph, which is also from the same two calibrators, things get a little stranger when you get into very low pressures and into vacuum. So here are the same two calibrators. Again, calibrator A is percent full scale, it's the yellow line. Calibrator B is percent reading plus floor, which is the red line. Again, the y-axis is a spec error in PSI, and so the lower line is the more accurate line. Right around 0 psi, calibrator B is more accurate. However, over most of the rest of the range, calibrator A is more accurate. And so things are not always as obvious as the previous graph, and frequently, especially if your work is right around 0 to 1 atmosphere, either vacuum or pressure, you really have to draw these graphs in order to understand which one will be better for you. This is something that you shouldn't expect a technician in the field to do. This is something that your measurement staff should really be doing for you and helping you decide. So let's go over a high-level procedural overview, and we're going to revisit calibrator A and calibrator B and talk more about test ratios. So at a very high level, the custody flow calibration looks very much like this. There's a setup, you isolate the valve and do a leak check. You'll take 3 measurements: differential pressure, static pressure, and temperature. The key thing to note is that the 2 pressure measurements are at very different scales. Differential pressure is frequently just a couple hundred inches of water, whereas static pressure is anywhere from 0 to, or even vacuum, up to 2,000 psi. And so frequently what will end up happening is that you'll need different ranges in order to do these measurements. There's also a temperature measurement. Pipelines tend to be in the ambient range, whereas wellhead temperatures can vary quite a bit depending on how deep the formation you're pumping out of. Last but not least, there's a return to service and cleanup. So we'll talk a little bit more about what all of that works. Oh, the other thing I'd like to mention very quickly, the key measurement is the differential pressure measurement. It supplies the largest component of error into the flow equations that would be in the back of those standards that we talked about earlier in the presentation. So let's talk a little bit about the unit under test. So the pressure device under test will has a range. It's usually determined at the time of manufacture and is also specified as a percent of input full scale. So we talked a little bit before about picking your calibrators to say, okay, it has to be as low as I can possibly get it. Well, the optimal thing to do is to actually match the range of your test equipment, because that is the lowest possible range. So if you're going to say do your calibration from 0 to 1500 psi on a Rosemount 3051, well, the best calibrator you would have would also be from 0 to 1500. Again, I talked before, you have two pressure ranges, you need two tools. One of the things manufacturers have done is they've actually combined two pressure ranges into the same tool. So there will be two ports, and there will be a low pressure port for the differential pressure measurement and a high pressure port for the static pressure measurement. These are frequently referred to as dual port electronic pressure calibrators. I'm not even going to try and make the acronym pronounceable, but there are several manufacturers who do those. I'm also going to define something called a test uncertainty ratio here. The test uncertainty ratio basically looks at the entire measurement system and says, okay, what are all of the sources of uncertainty in the system? Everything from the accuracy of the transmitter to the accuracy of the unit I'm testing. What about the skill of the person doing the calibration? What about the ambient temperature conditions? What about electromagnetic interference? There are all kinds of possible sources of error. And these are the sorts of things that your measurement staff or your metrologist would be working on. Now, in the metrology world, historically, a long time ago, 10 to 1, that is, your calibrator needed to be 10 times more accurate than the unit we were testing, was the standard ratio. Over the years, as both calibrators and the units under test got more accurate and more reliable, that number has dropped to 4 to 1. You see it's very common now in bench testing, so if you go into your measurement labs, you'll frequently see TURs of around 4 to 1. It's very common in nuclear and in the military, so the labs that they have will be in the 4 to 1. Unfortunately, it's frequently not possible. What we're actually seeing is that as the transmitters get more and more accurate, it's harder and harder for the calibrators to maintain that spacing. And so frequently you'll actually see TURs in the 2 to 1 or 3 to 1 range. So what does that mean? Basically, a lower TUR means that you are less certain in your results. So let's say that you perform a calibration and the unit is just barely out of calibration. It's just out of tolerance. So normally you'd say, oh, we have to do an adjustment. Well, if the unit has a low TUR, or if the calibration has a low TUR, you actually might not be out of calibration. The lower your TUR, the less certain you are that the unit, that your calibration was actually correct. So if you ran that same calibration again, there's a reasonably good chance that you might actually find that the unit is in calibration. And now you have a problem because you have an in-tolerance reading and an out-of-tolerance reading. Which one is correct? And so then it becomes very, very difficult to figure out, well, what do I do next? You know, is this reading valid or should I make an adjustment? This can be a very significant problem, and it's getting worse all the time. The last thing I want to mention, and we're going to talk quite a bit more about TURs, and I'm going to introduce a new term called a TAR here in a second. The last piece I want people to keep in mind is that if you have a flow computer with a milliamp input rather than a direct pressure or temperature input, you actually need to look at the accuracy of your transmitter's milliamp signal and your calibrator's milliamp signal as well, because you actually have that additional translation step that's occurring, and if your calibrator isn't accurate enough on the milliamp side, you're going to lose a lot of the advantage of your more accurate pressure measurement. So let's talk a little bit about high pressure test considerations. So one of the things that a lot of technicians we see in the field struggle with is keeping their units sufficiently clean. It's very easy to damage the seals. Manufacturers try to make them as rugged as they can, but a lot of times technicians will use process pressure or flow pressure in order to pressurize the units up because they don't really want to do the pumping because, you know, the pumping's no fun. But it's easy to contaminate your unit. If you're very, very careful, you can use things like drains and other traps in order to keep your unit clean, but it's frequently very, very difficult to do. One of the other things we'll often see is, especially on things like wet gas, is that you'll actually end up with liquids in the calibration cavities, and if you don't properly drain them, you'll end up with strange results, sometimes unrepeatable results. One thing we'll see a lot of people using, it varies very much by both region and by company, is that we'll see portable nitrogen bottles used to actually regulate the pressure. The idea here is that it makes the technician faster because they don't have to pump the unit up to pressure. They can just use the nitrogen bottle and the regulator to move between the various points. The downside is that the bottles do need to be recharged, and if you find yourself out in the field with a bottle that's not fully charged and you're trying to get to a relatively high pressure, you may not be able to get there. And so that it doesn't really give you any benefit. Some companies actually simply forbid it. They don't want the nitrogen bottles in the backs of trucks rolling around. So we've seen all types, but the one thing that's really important is that you really need to keep that bottle charged. The other thing that's going to happen is that nitrogen has a different Reynolds number than methane, and so you're going to have to make an adjustment for that during your calibration. Again, you're trying to eliminate every possible source of error. The other type of thing that I'd like to talk about very briefly is hydraulic test pumps. Hydraulic test pumps are another way of getting to very high pressures. Many of these hydraulic test pumps can get up to 10,000 psi. Assuming you're strong enough to get there. But it's very, very useful in that it's portable, lightweight, and it's always kind of ready to go as long as you have the DI water or the mineral oil that you'll need in order to accomplish what's getting there. It does not, however, prevent you from having to clean. You still have to clean up when you're done. It's possible to get mineral oil or water into the unit, and then you'll have to clean it. So this eye chart, this large graph, is actually what's called a TAR. So we talked a little bit before about TURs, which look at all the various types of uncertainty. A TAR, test accuracy ratio, really only compares the unit under test and the calibrator. Both of those things are specified by their respective manufacturers, and you can actually calculate a TAR quite easily without really thinking a great deal about the field conditions. The one thing to keep in mind is that because the TAR doesn't take into account a lot of the sources of uncertainty that a TUR does, a TAR is almost always better than what you'll actually see in the field. So again, remember we were saying that 4 to 1 is kind of the standard, although in the field 3 to 1 or 2 to 1 is more common. This is going to be, the graphs I'm about to show you are actually not as good as they appear. So again, this particular graph is for one calibrator compared to a particular transmitter. In this case, it's Calibrator A, which, if you may remember, was specified as percent full scale. I'm not showing you the graph for Calibrator B. The purpose of showing you this is just to say that this can actually be fairly complex. This one was built by one of our metrologists to compare Calibrator A with 4 different ranges, and you can see along the top here, range 2, range 3, range 4, range 5 of a Rosemount 3051C in this particular case. And basically, we ran through in order to demonstrate a point. And that point is these 4 graphs here. So these are the 4 ranges and calibrators A and B and where they fall out. And so the x-axis is the pressure all the way from 0 up to the upper range, so 10 psi, 40 psi, 350 psi, 2500 psi. And then the y-axis is the TAR. So what you're looking for is, in an ideal world, you're looking for better than 4 to 1. However, in the field, that's frequently not possible. So what you're looking for is the best over your entire range, but you're also looking for some other things. You're looking for simplicity. So you'll notice here that Calibrator A, which is specified as percent full scale, is a flat line, more or less. The line may have a slope, and there are some points that aren't quite as good as others, but in general, it's a pretty flat line across the entire range. Whereas Calibrator B, which is specified as percent of reading plus floor, actually its TARs change quite a bit over the range. And so while at the low end of the range, you actually have very good TARs, at the high end of the range, your TARs are significantly worse than calibrator A. And in many cases, they are actually below 2 to 1. Keep in mind also that the TAR is better than what you'll see in the field. And so if you're calibrating at the high end of the range, especially if there are other sources of uncertainty, you're operating near the edge of the temperature range of the calibrator, you are trying to make a very careful measurement and you have other sources of error, it's very, very possible that you could end up with a result that has only a 30% chance of being, or excuse me, you could end up with a result that has a 30% chance of being incorrect. And so one of the benefits is of a specified as percent full scale is that when you get an out of tolerance, you have a fairly good idea of how likely it is that that measurement is, or that calibration is actually the correct one. Whereas if you are using percent reading plus floor, you're actually going to need to calculate what the TUR was for that particular point and say, okay, where am I? How uncertain am I? If you're near the upper range, you know it's worse, but you'll notice that the graph is curved. It's not linear, so you can't just calculate 2 points and interpolate it. You've got to calculate the whole thing. So this is one of the key disadvantages of percent reading plus floor. While it gives you a great deal of accuracy at the low end of the range, it takes it away at the upper end. And so that's kind of the trade-off you have to make. As the transmitters themselves become more accurate and the calibrators are closer and closer to the line of good enough, what ends up happening is that this is starting to be something that an individual technician really needs to start asking for his measurement staff and his design staff to say, look, the calibration tool that you are using really needs to be specified when the transmitter is selected, because the measurement staff needs to support the design engineers with these kinds of accuracy and uncertainty analyses that actually allow the design engineer to say, okay, yes, that's good enough for this particular application. And then the technician needs to understand that the measurement team has actually looked at this and said, yes, this is the best possible tool combination that we can get, and we're going to go with this going forward. And you really have to kind of build your procedures around it. We're not seeing a lot of this in the field, and it's one of the biggest misunderstandings that we run into. So we're going to talk about a little bit now, we're going to go on to sort of what I would call the curriculum topics here at the end. So we'll talk a little bit about flow computers. The main thing I want to cover on this page is that there are two types. They're direct and indirect, and we kind of already touched this before. Direct computers will have pressure and temperature measurements made directly into the device. You're going to need your laptop if you're going to do an adjustment. Frequently it's easy to do your as found. This is the most common type that we see. There are a fairly large number of installed base of indirect input computers that actually will convert those measurements into a milliamp signal. The milliamp signal is what's fed into the flow computer, and therefore you actually have to require an accurate measurement of your milliamp signals. The other thing about the indirect method is that it's not uncommon to see ones that will require HART. And so if you need HART, you need to make sure you pick either bring a HART communicator like an Emerson 475, or have a unit that can at least communicate HART and do the work that needs to be done for you. So let's do a sort of high-level overview of what a procedure would look like for a custody transfer calibration. So obviously your local procedure will dictate what kind of safety equipment, PPE, other steps that you need to take prior to going into the area. We're not going to cover that because every company is different, but it's important to mention and keep in mind. The very first thing you're going to do is an isolation and leak check. So the unit will have valves that will isolate it from the process. You'll close those valves. You'll wait. You'll attach a gauge or something similar to the unit. You'll wait at least 30 seconds, and what will happen is you're looking to see if the pressure changes. You're going to look at the DP, and if the DP goes negative, at least under most circumstances, you'll actually have a high side leak. and it'll be positive if you have a low side leak. This is only when the unit is isolated from the process. If you have no or low flow, you may have other problems, especially for a differential plate or differential pressure meter. They're really not designed to go much out of their 3-to-1 or so turn down ratios, and if your flow conditions drop outside, it's very easy to see zero drift. So this rule of thumb only operates when the unit is isolated and you're doing a leak check. You're going to do a little bit of data recording, so pretty much you're going to do your as found zero. A lot of times this will be with your laptop if you have a direct method, and then you want to record this as quickly as you can, and then you want to record this and as quickly as you can move into your test. You don't want to have a lot of time between when you record the data and when you perform the test because it allows for error to seep in. You're going to record your transmitter data after each particular verification or adjustment step because you really want to not forget it. If you forget it, you're more likely to write down the wrong thing and make a mistake. One quick note here, there are certain calibrators, documenting process calibrators, that will actually do all of this recording for you automatically. Fluke does make one. There are other manufacturers that make them as well. These things give a couple advantages. One is that it means you don't inadvertently skip any steps in the procedure, and two, it ensures that the technician doesn't have to write the data down, which makes his life easier, but also that the data is not, there are no errors in recording, and then that can be documented with tracking software, which feeds back into the main purpose of this, which is to maintain accurate calibration records in case of a dispute. Your records can protect you from being accused of not or of manipulating your transmitter. So let's move into the actual test itself. The differential pressure test tends to come first. You're going to do, again, an as-found transmitter zero. You'll connect the unit to the low pressure side, so your calibrator will go to the low pressure side of the flow computer. So you've got an example here of one particular setup. That particular diagram doesn't show a pressure source, but there would be a pressure source between the low port on the electronic pressure calibrator there and the transmitter. You will, a lot of times you'll have to, if you're using a direct transmitter, you'll have to log in via your PC, and then you'll basically use the pump in order to get through your various checkpoints. It's usually 3 to 5 points, 0 to 100%, and this will be a very small pump. So you'll probably use a pneumatic pump for this, and you'll use a relatively small one. This is going to be just a couple hundred column inches of water. Typically what we find here is that 0.1% variance is going to give you an out of tolerance. If you are out of tolerance, you're going to have to adjust. You should have a local procedure that tells you how to do this adjustment. Again, each setup is different, so I'm not really going to spend a lot of time and go into that. Moving on to the static pressure transmitter test, it's going to look very similar. Instead of being on the low pressure side, though, you're going to be on the high pressure side of the calibrator, and then you're going to connect it to the appropriate port of the transmitter, depending on if you have a 5 or a 3 or any of the other types of varieties that you see. If you're going to use a nitrogen bottle, you need to connect that. Otherwise, you're going to use probably her hydraulic pump. It's pretty uncommon to see pressures, especially once you actually get into the pipeline world, where it'll be low enough that you can actually use a pneumatic pump. And so you'll have to make sure that's set up and attached. Typically what we'll see is that you're going to check 0 and 50% of the span, and you'll basically compare that with the flow computer reading. If you're about 0.1% out of away from what the flow computer says, you're going to get an out of tolerance, and then you basically have to go all the way, all 5 points from 0 to 100. You're going to end up doing an adjustment. Again, it's per the local procedure. It depends very much on your particular flow transmitter transmitter flow computer combination, and then you're going to repeat that verification in order to make sure that your adjustment was correct. The last test is the temperature test. Temperature actually is kind of interesting in that, despite the fact that it's the least important of the measurements in the gas custody transfer measurement, calibration measurement, it actually tends to be the most complex. It depends very much on your flow rate. If your process is shut down, you can check it directly using the RTD. If you have it shut down, you pretty much are going to have to use an RTD simulator and it's best if you can do it in conjunction with a dry block or a bath like we talked about earlier. So if you have good flow through the system, you're going to simply use your RTD. Here you see I've got a picture in the lower right-hand corner. That's actually an electronic pressure calibrator, dual-port electronic pressure calibrator that has an RTD input, so you only have to carry one tool. Really what you're going to do is you'll compare that RTD reading with transmitter reading. If you see a variance, typically we'll see about 0.2% Fahrenheit, but less than 0.5% Fahrenheit. You're going to end up re-zeroing the transmitter, but if you're more than 0.5% Fahrenheit off what the transmitter says, you're going to actually need to go in and do an adjustment. Under low flow conditions, you'll use an RTD simulator, and then you'll do a 3 or a 5-point check depending on your local procedure over the full span of the transmitter. The variance criteria don't change though. If you're less than 0.2, you're good. 0.2 to 0.5, you're probably going to re-zero the transmitter. Greater than 0.5, yeah, you're probably going to have to make an adjustment. Your adjustments per the local procedure. Frequently what you're going to do is you'll actually use something like a super thermometer, a very high accuracy thermometer in order to do that adjustment. It tends to not be as common. Usually where you get into trouble is the differential pressure measurement. Last but not least, if you did the adjustment, you are going to have to go in and do a post-adjustment verification in order to make sure that you have done your adjustment correctly. Okay, so if there are any questions or comments, you can email the moderator. If you have further questions, you can call Transcat, or you can find the application note that this presentation was drawn from, and further product information at transcat.com/Fluke Oil and Gas, all one word. That concludes the main portion of today's topic, and thank you very much.